Hello, I'm Ardra. This will be the second class of physical chemistry, and this will be the second class in surface chemistry. In today's class, I'm going to discuss about the adsorption isotherm. There are different adsorption isotherms in chemistry. In today's class, I'm going to discuss about the two of them: Freundlich adsorption isotherm and Temkin adsorption isotherm. So first, we are going to see what is adsorption isotherms, adsorption isobars, adsorption isosteres, and these three of them. So first, what is adsorption isotherm? The graph between the amount of adsorbate X adsorbed on the surface of the adsorbent versus the pressure at a constant temperature is called adsorption isotherms. So any graph that is drawn at constant temperature, we call them as isotherm. So if we, in case we are drawing the graph of adsorption at constant temperature, we call them as adsorption isotherm. So here is the graph of is the adsorption isotherm. It is drawn by X by M versus pressure. X by M, that is the amount of adsorbate adsorbed on the adsorbent surface versus the pressure at which the adsorption occurs. Here, the two such graphs are given at two different temperature. Temperature is maintained constant, but different graph of two different temperature is given here. There is T2 graph and T1 graph. T2 is greater than T1. We know that adsorption is an exothermic process. So when the temperature increases, desorption will be more common. So at a T2 temperature, the mass of adsorbate adsorbed is less compared to T1 temperature, which is lower than T2. Next, we are going to see about adsorption isobars. The graph that is drawn between the amount of adsorbate adsorbed on the adsorbent surface versus the temperature at which the adsorption occurs is called adsorption isobars. At constant pressure, any graph that is drawn at constant pressure is called isobars. When we draw graph of adsorption, it is called adsorption isobar. So the graph is drawn between X by M versus temperature. Here also, two graph is drawn at P1 and P2, two different pressure. P1 is greater than P2. The upper graph is of P1 and lower graph is of P2. We can see that at higher pressure, more adsorbate is adsorbed on the adsorbent surface. So we also know that when pressure increases, the adsorption also increases. So we can conclude from this graph that when temperature increases, the adsorption decreases, and when pressure increases, adsorption increases. Next, we are going to see about adsorption isostere. The graph that drawn between the pressure and temperature at which the adsorption occurs at a constant mass of adsorbate adsorbed on the adsorbent surface. Here, what we are making constant is the amount of adsorbate adsorbed. So the graph is drawn here at a different volume of gas adsorbed on the solid surface at V1, V2, V3 and V4. Here V4 is greater than V3, V3 is greater than V2 and V2 is greater than V1, and lowest is the V1, and the temperature versus pressure graph is drawn here. Such graphs are called adsorption isosteres. Next, we are going to see detail about adsorption isotherms. The process of adsorption is mainly studied using the graph known as adsorption isotherm, because the pressure have a major impact on the adsorption process. So mainly the adsorption process are studied using the adsorption isotherm. This is a typical adsorption isotherm drawn here, that is drawn against X by M versus pressure. And we are also seen in the last class that PS is the saturation pressure, the pressure at which the adsorption is maximum. After that pressure, when we increase the pressure, there will be no change in the amount of adsorbate adsorbed on the surface. In adsorption, adsorbate will get adsorbed on the surface of the adsorbent. The equilibrium will shift to the direction where the tension can be relieved. So we know that from Le Chatelier principle, if a system is in equilibrium, when we increase the pressure of the system will try to reduce the impact of that pressure on it. So when adsorption occurs, adsorbate will get adsorbed on the adsorbent surface and adsorption will occur. So at the reaction side, two type of molecules is present, and in the product side, only one type of molecule is here. So when we increase the pressure of the system will try to reduce the pressure by reducing the number of molecules. So the number of molecules decreases in the forward reaction. So forward reaction of equilibrium is favored. So when the pressure of the system increases, system will try to increase the rate of forward reaction. So adsorption will be occur at a faster rate. Next, we are going to see about the different type of adsorption isotherm. There are Lagmar adsorption isotherm, Freundlich isotherm, BET isotherm, Dubinin-Radushkevich isotherm, and Temkin isotherm. In this class, I am going to discuss about Freundlich adsorption isotherm and the Temkin adsorption isotherm. So, first is Freundlich adsorption isotherm. In 1909, Dr. Robert Freundlich proposed Freundlich adsorption isotherm. This estimates the adsorption intensity of adsorbent towards the adsorbent surface. In this theory, it is considered that it is considered that there is inhomogeneity in the surface, in the sides of the adsorbent surface. So it says that these different sides, adsorption sides of the adsorbent surface is heterogeneous. That is, all these sites are not homogeneous, not equal. So adsorption will occur at a different rate, and it is only an empirical expression, not an experimental one. And it considers the surface roughness, that is inhomogeneity, and also consider the adsorbate-adsorbent interaction. That is, it will be this graph will be different for different adsorbate and adsorbent. It will be specific for only one type of specific for different surface. So first, we are going to discuss about the graph, the typical characters of the graph of Freundlich adsorption isotherm. Here, the graph is drawn against the variation of extent of adsorption with the pressure. Here we can see that X by M versus pressure graph is drawn. At low pressure, that is the starting point of this graph, it shows a straight, it almost behave like a straight line. That is, when pressure increases, the mass of adsorbate absorbed on the adsorbent surface also increases. So it is directly proportional. So X by M is proportional to pressure at low pressure, and so X by M, when we when we multiply a constant, we can see that X by M is equal to Kp. Here X by M is proportional to P raised to 1. So X by M is proportional to the first power of pressure. But at higher pressure, we can see that even though when we increases the pressure, there is no rapid change in the mass of the adsorbate absorbed on the adsorbent surface. So at higher pressure, the graph become almost constant. That is, it become almost parallel to the x-axis, that is the pressure axis, which means that X by M will become independent of the pressure. So it may be expressed as X by M will be a constant and X by M will be proportional to P raised to 0. Pressure has no effect on the mass of adsorbate absorbed on the adsorbent surface. So X by M is equal to K into P raised to 0. Pressure has no effect on the rate of adsorption at higher pressure. So that there will be no adsorbent surface available for increased adsorption. All the sites in the adsorbent surface will be used up by the continuous adsorption process. So there will be no further adsorption will occur. In intermediate range, the range of pressure, that is between the point A and B, X by M will depend upon the power of pressure at some extent, but at low pressure, the pressure will be directly proportional to adsorption, and at high pressure, the pressure will be independent of the mass of the adsorbent absorbed. So at an intermediate range, the power of pressure will be lies between 0 and 1, that is between 0 and 1. Between this graph, it is a fractional power. It will be proportional to some fractional power of pressure. This may be expressed as X by M proportional to P raised to 1 by N. And when we multiply a constant, we can say that X by M is equal to K P raised to 1 by N, and will be characteristics of a specific adsorbent and adsorbate. It will be a characteristic for a pair of adsorbate and adsorbent, and will be a whole number, so that we can get a decimal power of P. So that graph is almost a sigmoid curve. If we want to get a linear form of Freundlich adsorption isotherm, we have to take the log of both sides. In the common general form of the Freundlich equation can be written as x by m equal to k p raised to 1 by n. If we want to make a linear form, we have to take log on both sides. When we take log on both sides, log x by m is equal to log k plus 1 by n, that will the power will become should be multiplied to the log of p. So when we draw the graph of log x by m versus log p, we can see that the slope of the graph will be 1 by n. 1 by n is multiplied to log p, so it will become the slope, and the factor that is added to the 1 by n log p, that is log k, will become the intercept. So if we draw the graph of log x by m versus log p, we can see that the slope of this graph is 1 by n, and it will be characteristic for a specific adsorbate and adsorbent pair. And the intercept, from the intercept, we can see that it will give the log k, that is constant, equilibrium constant of the adsorption process. Next, we are going to discuss about the limitation of Freundlich adsorption isotherm. Freundlich equation are purely empirical. We have discussed in first section. Is purely empirical and have no theoretical basis. The equation is valid up to only a certain pressure and invalid at higher pressure. It is not, we saw that the pressure have no dependence on the rate of adsorption at a higher pressure, and it's only valid to some certain pressure range. And the constant K and N will vary with temperature. We also see that in the adsorption isotherm, there will be different graph for different temperature range. So K and N, that is constant, we considered in the Freundlich equation, will also vary with temperature. Then next point is Freundlich adsorption isotherm fails at higher concentration of adsorbate. When there is higher concentration of adsorbate and a limited sites in the adsorbent surface, this equation will fail to fail in the equation will fail. Next, we are going to discuss about Temkin adsorption isotherm. Temkin equation was proposed first to describe the adsorption of hydrogen on platinum electrode in acidic condition. The basic assumption of this adsorption isotherm is it is mainly useful for chemisorption, that is chemical adsorption processes. The adsorption, here we consider the adsorption heat of all molecule decreases linearly in coverage of adsorption surface. We saw that it is the adsorption is a exothermic process. There will be a release of heat when a gas molecule get adsorbed on the solid surface. Here, when the adsorption process proceed in the forward reaction, there will be a considerable decrease in the adsorption of heat of all molecule. Then the decrease will be linearly in further coverage of the adsorbent surfaces. And it also say that the uniform distribution of binding energy. There will be a uniform distribution of the adsorption side, and the binding energy of the gas molecule toward the solid surface will be binding energy will be uniform. Next, we only have to understand the equation of the Temkin model. Here, QE is equal to BT ln KT plus BT ln C. This is the equation of Temkin model. Here, Kt is the equilibrium binding constant, and Bt equal to heat of adsorption. It is already said in the assumptions about the heat of adsorption of each molecule. So Bt here we consider as the heat of adsorption, and small bt is the Temkin adsorption constant, and it is related to the variation of adsorption energy. And here QE is the same as x by m. We have seen in the previous Freundlich adsorption isotherm a term called x by m. It is same as QE. And CE is the equilibrium concentration of the adsorbent in the solution after adsorption. And QE is the adsorbate adsorbed per unit weight of adsorbent at equilibrium. And the BT can be derived from the small bt equation by BT is equal to RT by BT, and R is the gas constant and T is the temperature at which the adsorption occur. So when we draw the graph of this model, we can see that QE is equal to QE from this graph, QE versus LNC graph is drawn here. So here this slope will be BT and the intercept will be BT, ln, KT. So the drawback of this graph is only cannot be used for complex system. Only simple system can be on this equation can only be applied to simple systems. That will be end of this class, and we will discuss about the rest of the adsorption isotherms in the next class. Thank you.